Yeah, thank you, Emil, for a very kind introduction. Thank you all for joining today. And my purpose today is to give you an overview of what short packet or finite block length information theory is about and how it can be used to design next generation wireless system. And the idea is that maybe you will find this interesting, get curious, and maybe this will become a tool among the tools you use for your research. All right. Okay, so the motivation for this theory is help us design in real-time distributed autonomous system. To support those systems, we need the new kind of connectivity that is able to allows us to connect to a massive number of devices, often operating under stringent energy efficiency constraint, and you need to transmit short packets, sometimes under stringent reliability and latency constraint. And the need to support this traffic is well understood in the context of cellular communication, right? We have, since 5G, two new use cases, machine type communication, massive machine type communication, ultra reliable low latency communication, which are essentially targeted and supporting this kind of connectivity. But the activity goes well beyond cellular system. There's a lot going on in the license-free part of the spectrum, with solution coming from many players, mainly targeting the massiveness of the access. And of course, when we talk about massive access, there are by now also satellite-based communication solutions that are becoming increasingly interesting. So what do we want to do, and which kind of connectivity are we thinking about providing? Well, the idea is to exploit the increasing amount of computational power that is available at the network edge to implement their distributed autonomous system. Now, if you think about this, this computational power, as a brain implementing a distributed system, what does this brain need? Well, it needs two things in my mind, right? It needs timely input from a large number of sensors that helps this brain figuring out the reality that brains wants to influence and control. So it needs sensory input, okay? And if you think about the connectivity, which I depicted in blue, that is needed to provide this kind of sensory input, well, we are thinking about mostly uplink communication. We're thinking about high energy efficiency in the communication link, because those sensors might be equipped with batteries. We want to deploy them and leave them in the environment. We don't want to touch them. So energy efficiency is the key, same as our nerve system. Allows us to gather information in a very energy effective way, right? But once we have gathered this information, once we have made sure that the reality we want to influence is well described in the network, in the computation available in the network, then we want to influence the system. To influence the system, we need bidirectional links, right? That send control signal, that send information to actuators, right? So this is what I depicted here in orange. And this kind of connectivity is completely different, right? We want it to be bidirectional. We want it to be low latency and high reliability, right? Okay, so let me discuss these two kinds of connectivities and highlight what is similar among them and what is different. Okay, so if we think about massive machine type communication, right? So here we are gathering sensor information. We think about short packets, maybe 100 bits. We are thinking of very high user density. So say, 1 million of device per square kilometers. These are numbers that we are thinking about in the context of massive machine type communication. But sporadic transmission, most of the time those sensors are not really transmitting. Maybe there's one transmission per minute. And now if you do your math, thinking about 20 megahertz bandwidth system, then what you are left with essentially 120 degrees of freedom per user. That's what you have at your disposal to design such a system. Okay. So now if you move to the other setup, bidirectional high reliability, low latency communication, then again, typically a small information payload. You're thinking about sending commands. So a few bytes are enough to describe a command, right? Low latency, especially in factory automation scenario, this can be as low as 100 microseconds. And low error probability. We think about this 5.9 reliability, which gives a 10⁻⁵ error probability, right? And again, if you do the similar exercises here, thinking about a 5G system with a subcarrier spacing in 5G, then again you are left with essentially 168 degrees of freedom, 2 resource block per user. Okay. So the key design question, if you want to abstract this away a little bit, in my mind, is how to transmit hundreds of bits in around hundreds of degrees of freedom per user under stringent constraints. Could be reliability and latency here, could be energy efficiency here, right? That's the fundamental question that one wants to address. And that's what I call the short packet regime. So for me, the short packet regime is the regime in which you're given 100 bits and you want to deliver in 100 degrees of freedom per user. Okay. So how do we design system operating in this regime? Well, this regime is quite different from the one for which we have designed broadband systems, right? And the tools that we have there are not necessarily good enough for this regime. So the tool that is by now well understood to work well to design such system is finite-blocklength information theory. So that's the tool. So what is it and why is it that in asymptotic information theory is not enough? Well, in a nutshell, asymptotic information theory gives us this picture. Okay, so if I have a noisy channel, through optimal coding, in the limit of large packet size, I can transform this noisy channel in a bit pipe, in a pipe that let bits through in a noiseless fashion, provided that the rate at which I try and push those bits through this pipe is no larger than the channel capacity C. Okay, so that's the asymptotic abstraction on the physical layer that is provided to us by asymptotic information theory. That's of course very useful for many reasons. One, it provides a benchmark on performance. So we know that if we operate close to C, we're optimal, and there's no way we can push a system operating above C, right? So it gives us fundamental limits, it gives us a benchmark. It's also very useful to design algorithms, right? Because it abstracts away all the details of the physical layer, coding, modulation. It just replaces it with a number, which we can use in the design of algorithm operating above the physical layer. User scheduling, resource allocation, power control, right? And often, actually, in practical application, we are not really interested in knowing C. We are perfectly fine with lower bounds on C, which capture certain feature of the system we are interested in. For example, imperfect knowledge of the channel, simplified processing of the information that we have at the transmitter and the receiver to account for, constraints in terms of complexity. So lower bounds on capacity, for example, the one of the form expect the log 1 plus SINR that most of us are using regular in our research, are actually very useful from a practical perspective. Okay, what breaks here? A sufficiently large number of channel uses. This asymptotic limit entails sufficiently large number of degrees of freedom per user. And in the short packet regime, we don't have sufficiently many degrees of freedom per user. We have around 100. And 100 is not large. When we say sufficiently large, we think about 1,000, 10,000. That's the typical number that we need to approach capacity, but depending, of course, on the error probability and the SNR we are interested in. Here we are 1 or 2 orders of magnitude less. So this theory is not precise enough. Okay. So what I want to try and show you in this talk, well, I'm going to ask the simple question, like, what should I replace this expected log 1 plus SNR formula? What should I replace it with if I'm interested in operating in the short packet regime? And I want to give you a recipe. What should you use? Okay. And now, when I'm seeking this expression, I want a few things. I want the expression I'm replacing this quantity with to be accurate. So it needs to be grounded in information theory. It needs to give me a precise characterization of the quantities I'm interested in, error probability, rate. It should be fairly easy to evaluate numerically, because I would like people to be able to design algorithms on top of it, operating at higher layer, right? And it should be applicable to realistic wireless networks, right? I don't want a formula that works only for a noiseless or a binary symmetric channel. I want to have a formula that I can apply, to a massive MIMO setup or to distributed MIMO setup. Okay. Okay, so let me tell you a little bit about how such formulas are obtained, how they are computed efficiently numerically, and how we are going to make sure that they're applicable to scenarios of practical interest, okay? And I won't just set up a few notation I'm going to use in the remainder of the talk, so that we're all on the same page. And to do that, I'm going to look at this simple channel coding problem you're all familiar with. Okay, so we have a message, a bunch of bits, right? And I describe this message as a number between 1 and m. So I need log m bits, log to m bits to describe it. Okay, so this message is mapped into n symbols and complex channel uses. You can think of n as the number of degrees of freedom or time frequency slots over which you are going to transmit your m, your message w. This block goes to a noisy channel. I get a received vector consisting of a noisy observation of what I transmitted, and I use them to estimate my message. So the key quantities I'm going to be interested in is the error probability, the probability that the message I decode is different from the message I transmitted. So that's a packet error probability. It's not a bit error probability. If one of the bits is wrong, the entire message is wrong, right? So it's a packet error probability. And then the rate, which is the ratio between the number of bits that I need to describe one message and the number of channel users I use to convey that message. Okay, log m divided by n. And what I'm interested in is, you know, if you give me a packet size n and you give me a rate, what is the smallest error probability I can hope to achieve? Or conversely, you know, if I have a block length and an error probability, what's the largest rate at which I can transmit, right? If I can characterize one quantity, I know the other. Okay. All right. So characterizing these two quantities, the problem is as old as information theory. Okay. Indeed, the first attempt to characterize these quantities date back to the work of Shannon, of Wolfowitz, Strassen, and then Gallagher and Lugushin. So talking about 50s and 60s, right? There's been a strong revival, a strong interest in revising this theory at the beginning of 2010 with the work of Hayashi and then Polyansky, and Verdú, who provided us with general bounds to characterize those quantities and very precise asymptotic characterization that go beyond capacity, okay? And then the relevance of this theory to the problem of massive random access has been pointed out in a very nice paper by Polyansky in 2017, and in the last 12 years, there have been many generalizations of this framework that are relevant for wireless fading channel. I'm going to show you a few of them, mainly biased towards the work that I've done, and mainly focusing on the ultra-reliable low latency regime. I won't talk much about massive random access. Okay. All right, so to give you a flavor for this bound, I want to plot them so that you see what they do and you see what kind of things we can get. And to plot them, I'm going to focus on a very simple channel, and then I'll make this channel more and more complicated as we go through the talk. The first channel I'm going to look at is simple binary input AWGN channel, okay? So you have BPSK symbols, +1, -1, you know, scaled by some SNR, you transmit it over the channel, which just add independent noise, okay? Now, what is the capacity of this channel? Well, it's not known in closed form, but it involves just a simple one-dimensional integral to be computed. So in particular, the capacity can be obtained by this maximum coding rate by letting the block length goes to infinity for any epsilon between 0 and 1. So it doesn't matter which epsilon you fix, you always converge to the same quantity. And if you have seen that in digital communication, if you want to compute the capacity of this channel, just have to solve a very simple integral that is related, you know, to the evaluation of mutual information for this channel, for the capacity achieving input distribution, which for a binary input AWGN is uniform over the two symbols. So it's a very simple, it's one line of MATLAB code if you want to compute this, okay, or Python code, whatever you prefer. The only thing that I want you to remember is that, you know, if you operate at an SNR of around 0.19, this capacity is equal to half a bit per channel use, okay? Okay, so let me try and then understand what is the relationship between, you know, the error probability and the rate. If we focus on the SNR, that is 0.189. So this gives me 0.5 bit per second, okay, capacity. So what Shannon tells me is that asymptotically in the block length, the the pairs epsilon r that can be achieved are all the pairs that are in this white region in the plot. Okay, so Shannon tells me that there's a fundamental limit, which I call channel capacity, and it's 0.5. And if I operate at the rate below 0.5, I can make the probability of error as small as I wish by choosing a block length that is sufficiently large. Right? Conversely, if I operate above capacity, actually I cannot get the probability of error that goes to 0, and actually you can show that the probability of error goes to 1 as you let the block length goes to infinity. So there's a sharp phase transition in the asymptotic limit and to infinity between rate below 0.5 and rate above 0.5 in terms of behavior of the error probability. Okay. Well, what happens if I give you 100 channel users? Okay. So 100 is different from infinity. How does this picture change? Right? And I'm going to tell you how it changes according to the best known bound for this setup. So this is how this picture changes. Okay. So the red region, I'm not sure if you see red in this plot, it should be reddish at least. This red region has increased. Right? Now I have a fundamental curve, which I call converse, is a red curve, which tells me that no matter how smart I am, I cannot find a coding scheme that operates at a rate and epsilon pair that is below this red curve. Okay. So you see, compared to the asymptotic, now we have to give up a lot of a bigger fraction of the plane in which we cannot really construct codes. Okay? And on the other side, I know that there exist codes, although they might be difficult to construct, above this blue line, this achievability line. Okay? And then there's a region between these two lines where I don't know if a code exists or not. There I give up. I don't know. And indeed, if I were able to exhibit a bound that would tell me exactly how to split this plane in two areas, I would have proven that P is equal to NP. So exactly finding a bound that distinguishes between what is achievable and is not achievable is an NP-hard problem. It's conjecture actually to be double exponential in the packet size. So even for n equal to 10, I don't know how to solve this problem for the binary input to WGA channel. Super hard. Okay, but from an engineering perspective, I'm not giving up too much, right? Now, if I increase n, well, what happens? The bounds start moving towards the asymptotic limit, and the gap between the two bounds shrinks. Right? This is 512, and this 1,000, 10,000. Okay, so we have a very good understanding from an engineering perspective how finite block length affect our ability to design code for a given pair epsilon r. Okay, so let me give you a feeling for how those bounds work. I'm not going to tell you how they are proven. I'm going to tell you what you need to do to compute them, right? And then we will see how to adapt those computations to the failing case. Okay. So the bound that I showed you is a version of the random coding union bound with parameter S. It's called RCOS. It's due by Martinez and Guilherme Fábricas and generalizes a previous bound by Poliansky-Cohen-Verdun. And it works as follows. You take the capacity achieving input distribution and you compute this log-likelihood ratio between the channel load to the power of S, and S is going to be an optimization parameters that we can tweak to make the bound tight, and an output distribution which is obtained by taking this channel to the power of S and passing through the input distribution. So that's what I called generalized information density. And now it looks a bit scary, but what you need to notice is that if you set S equal to 1, and you generate X and Y according to the joint distribution PY given XPX, what you get is the mutual information, and because you choose capacity achieving input distribution is capacity. Okay? So if you plug in S equal to 1 and compute the expectation of this, you get capacity. And for any S, you get something that is called generalized mutual information, which turns out to be a very useful quantity when you're interested in mismatch decoding. Okay? Okay, so that's all you have to do if you're interested in the asymptotic limit. You take this information density, you compute mean. But if you're interested in finite block length, you have to do something different. What you need to do is to generate as many pairs as your block length and start computing the accumulated information density that you observe over the packet and essentially evaluate the probability that a normalized version of this information density exceed a threshold that is related to the rate GP. Okay. So it doesn't matter what this formula exactly says. I put it up here in case you're interested in studying it later on. All you have to remember here is that in the asymptotic world, all you're interested in are mean values. In the finite block length world, what you're interested in are tail probabilities, okay, of related quantities. So we are computing tails. And it turns out that the converse works along the same principle. So it's a version of the min-max converse by Polyansky et al. It requires us to define another information density, which we call mismatch information density. But again, the converse bound entails evaluating tail of this normalized information density. Right? And now I have here, instead of the rate, I have the mean of this random variable. There's a bit of optimization that is needed. A very similar quantity. Both converse and achievability requires to compute tail. Okay, so what do we need to worry about if we want to compute those bounds? Okay, so you stare at them. Okay, I need to compute tail probability. What do I need to do? Well, first of all, I need to be able to generate those random variables. I need to be able to samples. So this requires me more or less, to be able to write the expression of defining those random variables in closed form, which might or might not be easy depending on which channel you give me. Okay, and then I need to compute tails, right? And tails, here I'm interested in very small error probability. So evaluating through Monte Carlo simulation those tails could be potentially very time consuming if you don't have closed form expression, and typically you don't. Okay, so what can you do? Well, because these are tails or involved in sum of independent random variables, one thing you can do is to apply a version of central limit theorem. So you could say, well, if you give me a sum of independent random variables, the probability that the sum exceeds the threshold is not too different from the Q function of a Gaussian random variable, right? And we know exactly what is the error that we do if we replace this probability by this Q function. This error is order 1 over square root of n. Okay, so if the probability you're interested in is not too small, this is not a bad bound. But because this probability decays exponentially fast in the argument, but this is just 1 over square root of n. If you insist on operating on very, very small error probability, this error might dominate, and then the bound is not tight. But whenever this bound is tight, what you can do is to replace it in those two expressions, fix the target error probability and solve for the rate. And if you do that, actually you can show that these two bounds coincide up to second order in the expansion of the block length and give you this nice formula, which is often used in finite block length. It's called normal approximation, which tells me that, in a nutshell, the maximum coding rate is equal to capacity minus a penalty term that depends on 1 divided by square root of the block length and depends on a new quantity, which is called channel dispersion, which is the variance of the information density. Remember, capacity was the mean. Now the channel dispersion is the variance of the information density plus error terms. Okay, so that's normal approximation. You want to compute for the BAWGN, right? You need an integral to compute the capacity, and you need a new integral to compute this variance. So these are 2 lines of MATLAB or Python code. Julia, I should mention else, I guess. I don't receive funding from any of those. I mention all of them and see who pays me in the end. No, I'm joking. And so they are very, very effective to compute. Okay. Now the problem is that for the reason I told you, if you insist on operating a very low error probability, then the error term might dominate. So here I plot the bounds that I showed you before, and in black is the normal approximation. So as you see, it's very accurate, provided the block length is sufficiently large, so the error term is small. Remember, that was big O 1 over square root of n. Or the error probability is not too big, so the Q is large, right? If you operate a very small block length and very, very small error probability, then the normal approximation has an error, okay? So what can you replace it instead? And this we understand very well. There's something in probability called the Saddlepoint approximation that allows you to evaluate very accurately tail probability. And the idea of the Saddlepoint approximation is very simple. I mean, if you have a tail probability and you want to evaluate it, and you know that this tail probability decays exponentially fast in some term. What you want to do is to extract this exponential behavior first, and then use a local central limit theory to approximate the prefactor. So that's the idea. If you want to do it rigorously, maybe some of you have seen this before, you need the cumulant generating function of the random variable you're interested in. And what the Saddlepoint approximation tells you that this tail probability is equal to an exponential decaying factor that depends on the point at which you want to evaluate this tail probability, and tau is related to the point at which you want to evaluate by solving this equation. So this is the term that you know, plus the term that you approximate as something that is obtained through a central limit theorem. So it involves a Q function and an error term. And now the beauty of this is that the error term is multiplicative. So it gets multiplied by an exponential factor. So this is also small. Okay. And indeed, this Saddlepoint approximation is super accurate. For block length as small as 20 is indistinguishable from the RCUS bound. And the only twist here is that you find two different Saddlepoint approximations, one for the achievability, one for the converse bound. And instead of computing two integrals to compute this for the binary input AWGN, you will need to compute three integrals, right? One for the first derivative of the cumulant, then the cumulant, then the second derivative. Those are the three integrals you need to compute. All the rest is known in closed form. Okay. All right. So that's all I wanted to tell you for this simple case. Oh no, there's one more thing that I need to tell you, right? Okay, so these bounds are nice, but can I approach them with actual codes? How far am I? Yeah, so here is rate 1/2 codes. 128 is the length. These are the bounds, achievability and converse, and these are some coding scheme. So this an LDPC code scheme that is for this CCSDS. So this is a satellite control channel. This, I guess, is the 5G LDPC code, BG2. That's a polar code similar to the one that is being chosen in 5G for the control channel. Operates already quite close to the bounds. And then we actually know how to approach those bounds. For this block length, we will need to use, for example, BCH codes or trellis byte convolutional code with sufficiently large memory decoded in a smart way to reduce complexity. So, the bounds can be approached with actual code. So if you know the bounds, you're in a good shape because you can describe codes that operate very closely to the bounds, and they're a good design tool. All right, so let me summarize this part, and then we move to the generalization. So what I try to convince you about is that for the simple binary input AWGN channel, we have accurate bounds. We know how to compute them efficiently, 3 integrals. That's all you need to evaluate. You need one to compute capacity anyways. And those 3 integrals are, if you want to have the most accurate approximation of the bounds, which is to the Saddlepoints. And those bounds are useful because we know how to achieve them with practical low complexity coding scheme. All right, so let me tell you what to do if you have fading in your system. Okay, fading. How should we think about fading in the context of short packets? Well, in the context of short packets, because we have low latency and sporadic transmission, it makes sense to assume that the system has no a priori channel state information. So if we want to have channel state information in the system, we need to use the resources to acquire it. For example, through pilot transmission, or if we have a reciprocity through a reciprocal channel that informs us about, who provides channel state information to the transmitter. And of course, in the context of information theoretic analysis of a fading channel, performance depends on how we assume that the channel varies across the packet. And here I'm using the simple Rayleigh block fading channel for this part of the talk, where I assume that the channel stays constant over a certain number of symbols, and I call the number of symbols over which the channel stays constant NC, and then changes independent from block to block. And I assume that a packet spans L fading blocks over which I can code across. So the length of the packet is the product NC times L, the symbols per block times the number of blocks over which I can code. And now I'm going to parameterize my maximum coding rate instead of with respect to the block length only. I'm going to parameterize with respect to both NC and L. Okay. And of course, if I'm asking about asymptotic limits, now I can play two different games. I can let n to infinity by letting L go to infinity and fixing C. Or I could let NC go to infinity but fix L to get n to infinity. So I have two natural asymptotic limits I can make this maximum coding rate converge to. Okay. And now, if you think about how do you get these independent fading blocks in the context of ultra reliable latency system in 5G, well, for example, you could spread your packet in frequency, and you could divide it in different frequency blocks that are separated more than the coherence bandwidth of the channel. So you space the subcarriers far apart enough so that those little blocks fade independently, something you can do in the downlink, usually not in the uplink because of transceiver design constraint. All right. So let us look at the asymptotic limits, and I'm going to try and convince you that if you try and optimize these systems of figuring out how large should NC be or L be for a given n using asymptotic limits, you get kind of contradictory insights. So if you let L to infinity for a given NC, then your maximum coding rate converges to the ergodic capacity for the case in which you have no CSI. Okay? And this ergodic capacity is not known in closed form, but we know how to characterize it fairly well. Essentially, B is essentially as the capacity when you have perfect CSI times a penalty term that accounts for the lack of channel state information of the receiver. Okay? So if you want to maximize this term, this formula will tell you, well, pick NC as large as you can, because then this preload will be small. Okay? And if you instead look at the outage world, right? Well, if you let NC goes to infinity for a fixed L, this goes to the outage capacity. And because NC goes to infinity, you get channel state information for free, right? Because if the block length is sufficiently large, you can learn the channel transmitting as many pilots as you wish with zero rate loss. And if you want to maximize this outage capacity, what you want to have is enough diversity. So you're going to try and make L as large as you can, right? Of course, you cannot do both. And the question is, what is reality? Where is reality, right? All right, you can solve this using finite block length once more, right? So you pick a PX that works, for which you can generate sample of this information density. And you write now those sum with respect to the blocks over which you code, right? So you have your achievability, you have your converse, and you have your saddle points. And if you stare at this problem long enough, you figure out that to compute the three quantities that you need for the saddle point, you need this time two-dimensional integral rather than one-dimensional integral, okay? And here is how the result looks like. So what I've done is to fix the packet size to 2 resource block, 168. I want to achieve 10 to the minus 5, and I have an SNR of 6 dB. And I'm asking, should I have longer blocks but fewer of them, or the other way around, right? So these two numbers always multiply to 168, which is my packet size. Okay. So as you see, if I plot here the achievability in blue and the converse in red, this is what I observe. If I insist on having no diversity and a large packet size, then the performance are very poor because I don't have enough diversity and it's very hard to get to 10 to the minus 5. And then, the performance increase as I increase the amount of diversity I put in the system up to a certain point. Then the performance goes down again because the coherence interval is too small and it becomes quite hard to track the channel. So very, very intuitive results, but we have a theory that tells us exactly for this toy channel model how to optimize things, right? And these bounds are still a little bit obscure because I'm using some, counterintuitive achievability result that relies on non-coherent transmission. What if I try and do things like actual system works? I try and estimate the channel elasticity transmitting pilots, and then I use the channel estimators perfect. Well, the bounds can be adapted to this setup. It's not too hard. So I need to define a metric that I want to maximize. And I'm going to assume that the channel is treated by the receiver as perfect. So this is the channel estimate. And I'm going to use a scale nearest neighbor decoding to find the code word that is closest to the received signal after I account for the fading. And you remember, to compute the RCUS bound, all we have to do is to evaluate this information density. But this information density required us to work with the channel law. So this information density, roughly speaking, corresponds to operating with the maximum likelihood decoder, the one that maximizing Py given X. All I have to do to consider this scale nearest neighbor decoding is to get rid of Py given X and replace it with the Q. Replace it with the metric I really want to maximize. And the bounds carry through. Everything that I told you is still true for this, at least from the achievability side, okay? So I can generate the bound to this setup, and now instead of having 3 two-dimensional integral, because I have this HF, I have 3 three-dimensional integral, okay? The complexity is increasing a little bit, but it's still manageable, right? All right, so what happens if I do this? So now I'm doing the same exercise as before. This time I fix the rate, and I'm looking minimum energy per bit that I need to achieve 10 to the minus 3. So I want this to be as small as possible. These are the 2 bounds I showed you before. And this is the new bounds that I get if I transmit pilots. So this is 1 pilot, this is 2 pilots, this is 4 pilots, 8 pilots, right? 8 pilots per block. So here I see how many pilots should I transmit per block to maximize performance. I see also the gap between an optimal non-coherent maximum likelihood detector and a practical. The beauty of this bound is that now if I take the coding schemes that I showed you before, and I evaluate the performance of a natural decoder, it can be shown to be roughly 0.5 dB away from these curves. So again, I know how to achieve these curves. Achieving this blue one is very hard, actually. Practical coding scheme, it's still something coding theorists are working on. It's not super easy. At this curve, we know how to achieve, and we have a few results. All right, so what does this slide says? Everything I told you for binary EWGN channel works also for point-to-point fading channels. Top of that, we can do channel estimation based bounds, and this still works. Okay, that's not quite enough, right? I have only 1 user in the system. I don't have multiple antennas. I have Rayleigh fading. It's all still based on a quite toy model. I want to make this theory a little bit more general. So what is missing? We want to apply it to the framework that you guys are working on, right? We want to look at massive MIMO. We want to look at linear spatial processing. We want to account for multi-user, residual multi-user interference. We want to account for the largest small-scale fading or realistic channel model. Okay, can we do that? Yes, we can. So I want to show you an example related to massive MIMO uplink. Okay, so here I'm estimating the channel matrix H, and I use it to construct linear combiners. So my channel model is going to be, the textbook channel model that Emil has described so well in his book. So this is the received signal from user U after combining, right? And I'm interested in a bound that holds a short packet for this setup, right? Now, what is tempting and has been done in the short packet literature is to take the SINR expression that you can find in, Emil's textbook or another textbook, right? Which are correct when we analyze asymptotic rate in the ergodic setup and plug that in normal approximation. So you take the normal approximation for a Gaussian channel and you replace the SNR with this SINR. And of course, although tempting, this approach is not correct because there's no way to rigorously relate this SINR to any notion of finite-blocklength rate if you're looking at a setup in which the channel stays constant over a packet, rather than you have an ergodic setup. So that cannot be done, unfortunately. So what we have to do is to pass through the bounds. But of course, if you have only one diversity branches, you're a bit in trouble because you don't have these blocks over which you can do central limit theorem-like analysis. So one way to resolve this is to implement simply IID Gaussian codebooks, which are the one we always evaluate bounds for, and then implement everything I told you on a conditional version of the zero probability, condition on the channel and its estimate. Now you can apply all the tools that I told you to evaluate this bound effectively, but then you need to do Monte Carlo over this H and HA. The beauty of this is that now H and HA can be whatever you wish. You You can generate channel from any model you wish. You can consider any estimator you wish. The bound still holds. But of course, there's a Monte Carlo step that is required. Okay. Alternatively, what you can do, provided you have at least 2 degrees of freedom, so 2 diversity branches in frequency, is to instead evaluate those Monte Carlo to compute those moments, those cumulants and derivatives in the Saddlepoint expression. And this turns out to be a way more effective way to implement those formula, but you need at least L equal to 2. And we have a recent paper describing this. All right, so let me conclude with the with the last few minutes with a couple of examples, in which I'm trying to show you how you can use those bounds in scenarios that are a little bit more, practically relevant to get insights. So now URLC should be supported with massive MIMO, distributed massive MIMO technology. So here's one scenario we consider. So we have 4 square cells, 10 users per cell, a base station with under antennas. And we have a very short packet, very short frame that we divided equally in uplink and downlink. Both in the uplink and in the downlink, we are transmitting just 160 bits. Okay, so the question we asked here was which type of spatial processing should be implemented, and how pilot contamination impact performance? Can we afford them? Can we afford pilot contamination if we look at ultra reliable low latency communication, right? And the performance metric I'm gonna use is what we call network availability. So here we consider many scenarios in which we drop the user uniformly at random. And the network availability is the probability that a randomly selected user among the one that I drop has a per link error probability below 10 to the minus 5. Okay. So I want this network availability to be as close as one as possible, which means that, for all the user drops that we consider, every randomly selected user had satisfied the URLC requirement. Whereas when this is small, of course, it means that I cannot satisfy in general URLC over the coverage area. Okay, so these are the kind of curves that you can get. So here, for example, we plot network availability as a function of the pilot length in both the uplink and the downlink. So we have 40 users in total. So below 40, we have pilot contamination if the pilot length is shorter, and above 40, we have no pilot contamination. And here we consider 3 kinds of receiving technique. So, we see here that as usual, maximum ratio combining doesn't quite work. So you have to go for more sophisticated processing. And you cannot really afford pilot contamination because performance drop. So you want to operate with a more sophisticated processing, linear processing algorithm, and you want to avoid pilot contamination. The downlink is based on channel hardening, so the performance on the downlink is worse than in the uplink because the UE need to rely on channel hardening to estimate the channel, and this is quite penalizing in the URLC regime, where we are quite sensitive to imperfection in channel estimate. Okay. Here is a cell-free, more recent experiment that we have done. So we have a little bit larger coverage area, but smaller and a smaller SNR, 40 users again. And here we are looking at access points that are regularly distributed in the coverage area, so in the grid, the coverage area. And we are playing with how many of those access points we're going to deploy, and we play also with how many antennas per access point we put. And the framework is the same as before. We have, short packet, 160 information bits. So the question we ask here is it better to go cell-free if we want to support URLC instead of going cellular when we deploy massive MIMO technology? And if so, how many antenna per access point should we deploy? And what about the downlink performance? We've seen that with the cellular massive MIMO, there's a performance drop. If we compare to the uplink, can we compensate for it using pre-coded downlink pilots? It's important to use pre-coded downlink pilots in cell-free. Okay, so these are the results we get. So this is the uplink. Now I have 2 blue curves, which is a cellular with one cell, and this is 4 cell. that covers the entire access point. And I have cell-free, both centralized and distributed. Centralized is in black, and distributed is in red. And on the x-axis, I have the total number of antennas in the system. So this is the product of the number of access points times the number of antenna per access point. Okay, so that's the total number of antenna in the system. I can decide how to split them between access point and antenna per access point. So what I see here is that the scheme that performed the best in terms of network availability, so that achieves the highest network availability for the smaller total number of antennas, is indeed cell-free. But among all the cell-free deployment I could consider for a given total number of antennas, the one that results in the best performance is the one corresponding to the case of single antenna access points. So in the ultra-reliable low latency regime, what you want really is to have an access point close to you that keeps the path loss as small as you can, because you are very sensitive to path loss in the short packet regime. Okay, so increasing the density of the access point is preferable than increasing the number of antenna per access point, but reducing the density of the access points. Whereas distributed, which is the scheme that performs the worst, actually requires access point with sufficiently many antennas, because there you need channel hardening to occur so that your distributed processing is accurate. Okay. So what about the downlink? The downlink is interesting because what we see is that if you don't do anything in terms of pilot transmission, the downlink, actually you should go for cellular with 4 cells. And yeah, actually distributed eventually outperforms it, although it doesn't achieve the network availability that you wish. And again, distributed would require many antennas per access point to work well. But if you start using pre-coded downlink pilots, then a cell-free works again. So the uplink and the downlink both show that cell-free with centralized processing is the best technology, but you need to use downlink pre-coded pilots to get satisfactory performance in the downlink in the scenario that we consider with short packets. And actually, you see that for the other 3 technologies, using downlink pre-coded pilots actually is deleterious. So the other 3 curves actually become worse if you put pre-coded downlink pilots, because here you're sacrificing code rate to add those downlink pre-coded pilots. So you lose rate and you don't gain much in performance. All right, so the message here is that the use of downlink pilots is critical in centralized cell-free, but actually superfluous if you go for distributed cell-free or cellular, because there you need enough channel hardening for the system to work, and then if you have enough channel hardening, you really don't need pilots. All right, so let me wrap up, and then I'll be happy to take on some questions if there's time. So the question I ask is, what should we replace expected log 1 plus SNR in the short packet regime with? And the answer that I suggest is, use the RCUS achievability bound with scale nearest neighbor decoding, pilot assisted transmission, and then evaluate this effectively using the Saddlepoint approximation. Right? And if you are interested, most of the MATLAB code that it's needed to reproduce the figures in this plot is actually available. And there are a few extensions I haven't talked about. I guess the biggest omission is all the recent work on random access that also relies on finite-blocklength. It shows that this theory is very useful also for those kind of systems. All right, and then I have slides with some references in case you're interested. All right, so that's all I have. Thanks a lot, and I'm happy to take questions if there's time.
Thank you.